This topic we're going to talk about integral curves. Let's look at these three polynomial functions. Y is equal to x cubed plus 2x squared plus 3. The second being y is equal to x cubed plus 2x squared minus 1. And the third, y is equal to x cubed plus 2x squared minus 3. And there's two questions. What do they all have in common? And how does that relate to what we have previously learned? If you think about it, they all have x cubed plus 2x squared in common. The second question, how does that relate to what we have previously learned? Well, they are all particular solutions to the differential equation dy dx is equal to 3x squared plus 4x. Let's analyze that a little bit further. Get my highlighter here. So our first equation, if I differentiate y is equal to x cubed plus 2x squared plus 3, I'm going to get dy dx is equal to 3x squared plus 4x. If I differentiate our second equation, y is equal to x cubed plus 2x squared minus 1, I'll get the same differential equation. Likewise, if I differentiate our third equation, y is equal to x cubed plus 2x squared minus 3, I will still get the same differential equation. dy dx is equal to 3x squared plus 4x. So these top three equations are a particular solution to this differential equation. When I say the word particular solution, you may want to also think of the word specific. They are specific to this general form of a differential equation. Now, this introduces a third question. How many particular solutions are there to a differential equation? And the answer is infinitely many. Since there are infinitely many solutions, all of the integral results in the same general solution are y is equal to x cubed plus 2x squared plus c, with c being the general constant of integration. The curves of just three of the infinite solutions are below. An integral curve represents the possible solutions to a differential equation, but cannot represent all of them. So the green curve is represented by the equation y is equal to x cubed plus 2x squared plus 3. The red curve is represented by y is equal to x cubed plus 2x squared minus 1, and the blue curve is represented by y is equal to x cubed plus 2x squared minus 3. Plus 3, minus 1, and negative 3 represent the y-intercepts of each of the curves. Now imagine if we drew small line segments to represent the tangent lines at many points on our integral curve. What would the results be? Imagine if we draw that well, the results would look like the following graph. You'll see tiny little slope lines at many points along the various curves. Now try to picture what it would look like if we erased the curves and just left the small dashed marks. It would look something like this. Notice without the actual curves graphed, we still can get a feel for what the general shape of this curve. Let's think back to the dinosaur fossils. So these would be like the bones of the curve, and if I move this curve, you'll see that as I move up and down the graph, the slope lines, the little dashed slope lines, do match what the curve looks like. If we add small slope segments to the rest of the graph area where the function doesn't exist, it would look something like what you see in this graph in the center of the picture. This is what we call a slope field. If you want to examine slope fields on your own, there's a link in this presentation that you can use. It's called the slope field simulation. To change the differential equation, click in the box below dy dx is equal to and type in the rest of the equation. To view different graphs that are possible for the differential equation that was typed in, click in the coordinate plane and a curve will appear. Continue clicking in the slope field to see more of the possible curves. I will demonstrate this for you. So you click on the link. And we have this open up. And our differential equation is dy dx is equal to x plus y. If I click anywhere in the coordinate plane, a graph will show up. And the more I click, the more different graphs show up. And you notice how each of the graphs follow the slope field of the small dashed slope segments that were created. If I click up here, and the ODE stands for ordinary differential equation, if I click in that box, a dialog box will pop up, and I can change the equation. I'm going to click and change it just so it says x. And I click in here, and what we see is a family of curves that seem to be parabolic, and there's a variety of different curves that were sketched in. And if I continue to click in the slope field, I get even more curves. And that would make sense because if the solution to the differential equation x would be x squared over 2, which is parabolic in nature.